Reality might be a single thread in an unimaginably vast tapestry. Every decision you make could be spawning entirely new universes at this very moment. This is the startling world of quantum echoes, the mysterious footprints of parallel realities. By the end of this exploration, you will possess a new framework for understanding the very nature of existence itself. We will investigate if bizarre particle behavior in labs is a whisper from another world, and ask if ancient historical mysteries are actually cracks between realities. What does it truly mean to be you in a cosmos of infinite versions? Our everyday reality, with its solid objects and predictable paths, is a comforting illusion. To find the true fabric of the cosmos, we must shrink our perspective down to the quantum realm, a domain where the ordinary rules of physics simply do not apply. The perfect starting point for this journey is one of the most famous and baffling experiments in all of science, the double slit. Imagine a barrier with two thin, parallel cuts in it. When you fire a stream of tiny particles like electrons at this barrier, you would expect them to behave like little bullets, each passing through one slit or the other and creating two neat bands on a detector screen behind it. But that is not what happens. Instead, the particles create a pattern of alternating light and dark bands, an interference pattern. This is the unmistakable signature of a wave, like ripples on a pond overlapping and canceling each other out. Somehow, a single particle is not just a particle, it is also a wave of possibility, passing through both slits at once and interfering with itself. The act of being observed, of trying to see which slit it goes through, forces it to collapse into a single, well-behaved particle, and the beautiful interference pattern vanishes. This bizarre duality lies at the heart of quantum mechanics, revealing a universe where things do not have definite properties until we look at them. This leads us directly to the principle of superposition. Think of a coin spinning rapidly on its edge. While it spins, it is not heads and it is not tails. It is genuinely both at the same time, a fuzzy blend of all possible outcomes. Only when it falls flat does it become one definite state. In the quantum world, a particle like an electron exists in a superposition of all its possible locations, energies, and spins simultaneously. It is everywhere it could possibly be, all at once. This is not a lack of knowledge, it is the actual physical state of the system. The great physicist Erwin Schrödinger famously illustrated the strangeness of this idea with his thought experiment involving a cat in a sealed box. The cat's life depends on a quantum event like the decay of a radioactive atom, which is in a superposition of decayed and not decayed. According to the math, until someone opens the box and looks, the cat itself is both alive and dead, a grotesque but logical extension of the theory. Schrödinger did not believe this was literally true. He created the paradox to highlight what he saw as a flaw in the prevailing Copenhagen interpretation, championed by Niels Bohr. This interpretation states that it is the act of observation itself that collapses the wave function, forcing the particle, or the unfortunate cat, to choose a single, concrete reality. But what if the wave function never actually collapses? What if every possible outcome implied by superposition does in fact happen? This is the door that quantum mechanics has unlocked, a door that may lead not to one reality, but to an infinite cascade of them. Before we step through, we must understand one more quantum phenomenon, entanglement, a connection so profound Einstein called it spooky action at a distance. When two particles become entangled, they form a single, linked quantum system. Measuring one particle, say, finding it with an upspin, instantly determines the spin of its partner, even if that partner is now on the other side of the galaxy. This instantaneous connection seems to violate the cosmic speed limit of light, suggesting a deeper, hidden layer of reality where distance is meaningless. These concepts, superposition and entanglement, are the fundamental tools we need. They show us that the solid, classical universe is a surface-level effect, emerging from a far weirder and more fluid quantum substrate. With this new vision of reality, we can finally ask the ultimate question: where do all those other possibilities, all those spinning coins that never land in our world, where do they actually go? Schrödinger's cat is neither dead nor alive in a single, paradoxical box. It exists in two separate, fully realized boxes. This is the radical solution proposed by a young physicist named Hugh Everett. His many-worlds interpretation suggests the wave function never collapses. Instead, at every quantum decision point, the entire universe splits. Every time a particle is in a superposition, reality divides, and every possible outcome plays out in its own newly created branch. There is no single path in the forest. You take the left path, and in that moment, an identical copy of you with all your memories and feelings takes the right one. Both of you are equally real, living in parallel universes that have just diverged. This happens not just for your big life choices, but for every quantum event, every flicker of possibility at the subatomic level. The cosmos is constantly flowering into a near-infinite multiverse of what might have been. This idea elegantly sidesteps the strange role of the observer. There is no mysterious collapse because every result physically occurs. The physicist David Deutsch champions this view, arguing it is the simplest and most straightforward way to interpret the mathematics of quantum mechanics. It removes the special, almost magical act of measurement. The implications for your own identity are staggering. With every breath you take, countless versions of you are being spun off into existence. A version of you who paused this video a moment ago exists somewhere. A version who chose a different career, a different breakfast, a different word in a conversation. So who is the real you? Are you just one thread in an unimaginably vast tapestry of selves? Films like Everything Everywhere All at Once have captured the sheer existential weight and chaotic wonder of this concept, making the abstract feel viscerally personal. Of course, a major criticism is that we cannot hop over to another branch and meet these other versions of ourselves. There is no direct, testable evidence for these other worlds. Yet for many scientists, the theory's mathematical elegance and its power to explain quantum weirdness without extra rules make it profoundly compelling. And it is within this framework of endlessly branching realities that we can finally begin to search for the echoes. If these parallel worlds are constantly splitting from our own, could they occasionally brush up against one another? Could the faintest whisper of another reality's choices leave a mysterious footprint in our own? But if every moment spawns new universes, why does our world feel so solid and singular? The answer lies in a subtle but powerful process called quantum decoherence. Think of a perfectly still pond, its surface capable of holding clear, distinct ripples. This is the pristine quantum world, a system isolated from everything else. Now, drop a single spot of ink into the water. At first, it holds its shape, a coherent droplet of possibility. But quickly, it begins to spread, its color diffusing and mingling with the water until the entire pond takes on a uniform, murky hue. The ink has lost its individual identity, becoming inextricably entangled with the countless water molecules around it. This is precisely what happens to a quantum particle in superposition. The moment it interacts with its environment, whether a stray air molecule, a photon of light, or the measuring device itself, its delicate wave function becomes entangled with trillions of other particles. This rapid, irreversible scrambling is decoherence. It does not collapse the wave function. Instead, it makes the different possibilities within it lose their phase relationship, their ability to interfere with one another. They effectively stop talking to each other. From our perspective, embedded within this tangled environment, the system appears to choose a single, classical state. The spinning coin seems to land. We perceive one definite outcome not because the other possibilities vanish, but because they fade from our view, continuing to exist in their own decohered branches of reality. Physicists like Wojciech have shown through intricate mathematics how this process is inevitable and incredibly fast. Experiments with increasingly large objects, like complex molecules made of hundreds of atoms, confirm this. In a highly controlled vacuum shielded from the environment, these large molecules exhibit wave-like interference, a ghostly superposition. But expose them to even a tiny amount of outside interaction, and that quantum behavior instantly vanishes, replaced by the predictable motion of a classical object. Decoherence is the mechanism that builds the comforting illusion of a single, concrete reality from the quantum soup of possibilities. It explains why you do not see your own coffee cup in a superposition of being on the table and on the floor. Its quantum states have decohered through constant contact with the air, the light, and your own hands. This theory beautifully complements the many worlds interpretation. It does not replace branching, but rather explains why, after a branch splits, we are completely unaware of our other selves. The branches have decohered from one another. They no longer interact, yet the question lingers. If these parallel realities are truly separate, carved apart by decoherence, could some faint, residual connection remain, like a whisper carried on a quantum wind? This is where the idea of quantum echoes emerges from the shadows of theory. If the multiverse is real, its countless branches may not be perfectly silent. Sometimes a whisper might cross the void. A quantum echo is a theoretical signal, a faint imprint left when parallel realities briefly interact or brush against one another. Think of it like a sound echoing in a vast, complex canyon. The original event, a quantum decision in another world, creates a vibration. That vibration might ripple through the fabric of reality and manifest in our own as a subtle, almost imperceptible anomaly. These echoes would be the mysterious footprints we are searching for, evidence that other worlds are not entirely separate from our own. So what might these footprints look like in practice? They could appear as bizarre, unexplainable glitches in particle accelerator data, where a particle behaves in a way that defies all known laws, as if it were being nudged by an invisible hand from another dimension. They might be tiny, spontaneous fluctuations of energy that appear from nothing and vanish just as quickly, a spark leaping between worlds. Some physicists have even proposed searching for patterns etched into the cosmic microwave background radiation, the afterglow of the Big Bang itself, as if the collective hum of infinite universes has left a signature on the oldest light we can see. Researcher Sean Carroll has thoughtfully explored how the fundamental mathematics of quantum mechanics might, in fact, permit a form of gentle communication or correlation between these branching worlds. It would not be a phone call to another you. It would be far more subtle, a statistical nudge, a shared tendency in the outcomes of experiments. Imagine a thought experiment. In one reality, you decide to turn left, while in another, you turn right. According to the many worlds view, these paths are separate. But what if the act of choosing left in your world sent a minuscule vibrational echo into the fabric of existence? In that other reality, the version of you who turned right might experience a fleeting, unexplainable sense of doubt, a feeling that the other path was somehow more significant. This is the ripple effect of a quantum echo, where a decision in one world leaves a faint emotional or probabilistic residue in another. The immense challenge, of course, is actually detecting such a whisper. Our reality is dominated by the deafening noise of decoherence, the process that constantly reinforces the solidity of our world and severs the links between branches. Finding a quantum echo would be like trying to hear a single, soft voice in a roaring hurricane. It would require incredibly sensitive equipment and a deep understanding of what to even look for. Yet this concept is a crucial bridge. It transforms parallel universes from a philosophical idea into something that could, in principle, be tested. It gives us a way to hunt for the footprints of other realities, not by traveling to them, but by learning to listen for their faint, reverberating calls in the data of our own world. The hunt for these quantum echoes has moved from theoretical papers into the harsh light of the laboratory. Teams of experimental physicists are now designing machines of breathtaking sensitivity, hoping to catch a glimpse of another reality brushing against our own. Their strategy is to probe the very edges of quantum behavior, looking for tiny deviations that have no explanation within a single universe. One frontier involves superconducting qubits, the building blocks of quantum computers. These artificial atoms can be placed in a state of macroscopic superposition, a delicate balance where they effectively exist in two states at once. Researchers meticulously monitor these qubits, watching for any subtle, unexplained shifts in their quantum oscillations. The hope is that the gravitational pull or quantum influence of a nearby parallel branch could nudge the qubit, creating a statistical anomaly in the data, a fingerprint left by a neighboring world. It is like listening to a perfectly tuned instrument for a note that should not be there, a harmonic from a universe out of phase with our own. At the most powerful particle accelerator on Earth, the Large Hadron Collider at CERN, scientists perform a different kind of hunt. They sift through the debris of countless high-energy collisions, searching for events that break the known rules of physics. A particle that appears from nowhere, a collision with missing energy that cannot be accounted for, or a statistical fluctuation so rare it defies probability. These are the anomalies that could signal an interaction with another reality. The data is overwhelming, trillions of data points that require immense computing power to analyze. The teams look for the proverbial needle in a haystack, a single event that might rewrite our understanding of the cosmos. Some of the most mind-bending clues come from refined versions of classic quantum experiments. The quantum eraser experiment, for instance, adds a profound layer of strangeness to the double-slit setup. In this experiment, scientists can mark which path a particle takes, destroying the interference pattern. But if they then erase that path information after the particle has already hit the detector, the interference pattern miraculously returns. It is as if the particle's past behavior is retroactively changed by a future decision. This apparent backward in time influence challenges our most basic notions of cause and effect. While not direct proof of parallel worlds, it hints at a reality where time is not the linear arrow we experience, a characteristic that could be essential for understanding how branches of the multiverse might communicate. The physicists leading these searches are the first to admit the immense challenges. They speak of the need for near-perfect isolation from environmental noise and the relentless demand for repeatable results. A single strange event is not enough. It could always be a simple error, a cosmic ray, or an undetected flaw in the equipment. The signal of a quantum echo must be so clear, so statistically significant that it cannot be dismissed. This requires instruments of almost unimaginable precision, pushing the very limits of our engineering and our patience. These lab-based quests are the rigorous, painstaking work of turning a beautiful idea into measurable fact. They represent humanity's most direct attempt to reach across the dimensional divide and touch another version of reality. Yet, for all their ingenuity, they are searching in a controlled, microscopic realm. If we want to find the grandest echoes, we may need to lift our gaze from the lab bench and look out into the cosmos itself, where the fabric of reality is stretched to its absolute limits. Our universe might not be a solitary island in the void, but one bubble in a frothing cosmic sea. To find the grandest echoes of other realities, we must look to the largest canvas of all, the cosmos itself. The most profound evidence could be etched into the oldest light we can see, the cosmic microwave background radiation. This faint, cold glow is the afterglow of the Big Bang, a baby picture of the universe when it was just 380,000 years old. Scientists have mapped this radiation in exquisite detail, and within its subtle temperature variations, they have found puzzling anomalies. One of the most famous is a mysteriously large cold spot, a vast region of space that is significantly cooler than the surrounding average. Within the standard model of cosmology, this spot is difficult to explain. Could it be a cosmic bruise, the imprint of a collision with another universe bubble in the distant past? Imagine a pot of boiling water with countless bubbles forming, expanding, and occasionally bumping into one another. If our universe is one such bubble in a process called eternal inflation, then a gentle nudge from a neighboring bubble could have transferred energy and left a permanent mark on its surface, a cold spot in the primordial sky. This is the kind of cosmic footprint theorists are searching for. Another tantalizing clue is known as the axis of evil, a strange alignment of features in the cosmic microwave background that seems to break the principle that the universe should look the same in all directions. This unexpected axis, a preferred direction in the cosmos, makes some scientists wonder if it reflects the gravitational tug or structural influence of a parallel reality lying just beyond the veil of our observable universe. Cosmologist Max Tegmark has elegantly categorized the possible types of multiverses, from the simple level one, where our Hubble volume repeats endlessly in space, to the more radical level 4, where the very laws of physics are different. If we live in a level 2 multiverse of eternal inflation, these cosmic anomalies are our best hope for a detectable signal. The echoes would not be subtle whispers here, but colossal scars on the fabric of spacetime. They might also manifest in the distribution of dark matter, the invisible glue holding galaxies together. Unexplained clumps or strange gravitational lensing effects could be the ghostly shadows of matter from another world. Or consider primordial gravitational waves, the ripples in spacetime from the universe's violent birth. A collision with another universe bubble would have sent powerful tremors through the cosmos, and our next generation of telescopes might be sensitive enough to detect the unique signature of such an event. These are not small laboratory glitches, but potential planet-sized fingerprints left by another reality. As we scan the heavens for these cosmic clues, we are forced to confront a deeper mystery. If other universes exist with different physical laws, then our own reality, with its specific constants that allow for stars, planets, and life, might be a rare oasis in a vast desert of inhospitable worlds. This line of inquiry brings us to one of the most profound and unsettling concepts in all of science, a principle that connects the infinite cosmos to the quantum realm and challenges our very sense of self. Einstein shattered our classical view of time with his theories of relativity, showing us it is not a universal river flowing at the same rate for everyone. He revealed time as a malleable dimension woven together with space into a single fabric called spacetime. Your own motion through space literally affects your passage through time, a phenomenon proven by atomic clocks on fast-moving jets. This relativity of simultaneity means two events that appear to happen at the same time for one observer can occur at different moments for another. This leads to a profound idea known as the block universe, where the past, present, and future all exist simultaneously in a single, frozen four-dimensional block. Your birth, your life, and your eventual end are all equally real, just located at different coordinates in this cosmic structure. This feels alien because our consciousness seems to slide along a single track from what we label the past toward what we call the future. But what if this flow is an illusion, a biological and psychological artifact rather than a fundamental law of physics? This concept of nonlinear time finds a strange partner in quantum mechanics. In the quantum world, the rigid arrow of time seems to soften. Experiments in quantum optics have demonstrated effects that border on retrocausality, where a particle's behavior appears to be influenced by an event in its future. In the famous delayed choice quantum eraser experiment, a decision made after a photon has already been detected seems to determine whether it behaved as a particle or a wave in the past. It is as if the photon's history is not fixed until later, a clear violation of our everyday cause and effect. The physicist John Wheeler, who devised this experiment, saw this as evidence for his participatory universe, a cosmos where observation does not just shape the present, but helps to define the past itself. So how does this relate to our branching realities and their echoes? If all moments exist in a block and the universe constantly splits at every quantum possibility, then the branching is not a process unfolding in time. The entire infinite multiverse of branches is simply there, a static, unimaginably complex structure. Within this framework, a quantum echo is not a signal traveling backward in time. It is more like a resonance between two adjacent branches in the block, a standing wave of correlation. Your feeling of déjà vu, that uncanny sensation of having lived a moment before, could be a faint conscious ripple from a nearly identical branch in the multiverse where you made a slightly different choice a second earlier. These are the feedback loops, the subtle imprints left when parallel realities which share a common past briefly harmonize. This perspective forces us to confront the final, and perhaps most personal, piece of the puzzle. If reality is a vast, timeless multiverse, and our perception of a linear present is just a narrow slice of it, then what is the true nature of the one thing experiencing it all? What is the role of consciousness in this layered cosmos? The very act of looking at the quantum world seems to change it, forcing a cloud of possibility to snap into a single, solid fact. This undeniable link between the observer and the observed brings us to the most intimate frontier of this mystery, the nature of consciousness itself. Does our awareness merely witness reality, or does it somehow play a role in building it? Some interpretations of quantum mechanics take the observer effect to its logical and startling extreme. The von Neumann-Wigner interpretation proposes that it is not the measuring device, but the conscious mind of the scientist that finally collapses the wave function. In this view, the entire chain of events, from the particle to the detector, remains in a blurry superposition until a conscious being becomes aware of the result. The universe, in a sense, waits for a mind to make a choice, to crystallize one possibility out of the quantum fog. This idea intersects with the many worlds interpretation in a fascinating way. If consciousness is what collapses the wave function, then perhaps it also acts as a filter, selecting which branch of the multiverse we personally experience. Imagine a vast, multi-dimensional camera with lenses pointing in every possible direction, capturing every conceivable version of a moment. Your conscious awareness is the viewfinder, and you can only look through one lens at a time. You choose, either deliberately or subconsciously, which snapshot becomes your reality. while the other images, the other versions of the event, continue to exist in their own fully realized branches. You are not creating the entire multiverse, but you are actively choosing your path through it. This is not just philosophical speculation. Eminent physicist Roger Penrose has theorized that the brain might harness quantum processes, perhaps within the delicate structures of neurons, to achieve consciousness. He suggests that gravity, acting on these tiny scales, causes wave function collapse, meaning our very thoughts could be rooted in the transition from the quantum to the classical world. If true, our minds are not just passive observers, they are dynamic participants, woven into the fundamental fabric of physics. This leads to a deeply personal and empowering question. If consciousness is a gateway, could we learn to intentionally access other branches? Could focused intention or profound meditation allow us to sense the echoes of our other selves, or even gently nudge our awareness toward a slightly different probability branch? The idea that our minds might be the key to navigating the multiverse adds a thrilling dimension to the search for quantum echoes. It suggests the footprints we are looking for might not only be found in particle data or cosmic radiation, but within the quiet architecture of our own thoughts. As we ponder the mind's profound connection to the cosmos, we must also turn our attention to the tools we are building, machines that are beginning to harness this quantum weirdness and are poised to reshape our world. The machines that could prove the existence of parallel worlds are being built right now. Quantum computers are not just faster versions of the device you are using. They are a fundamentally different kind of machine, one that directly harnesses the bizarre principles of superposition and entanglement to perform calculations. Their core component is the qubit. Unlike a classical bit which can only be a 0 or a 1, a qubit can be both 0 and 1 at the same time, just like that spinning coin. This is superposition in action. When you entangle multiple qubits together, their states become linked, and the entire system exists in a simultaneous combination of all its possible configurations. A system with just 300 entangled qubits can represent more states than there are atoms in the observable universe. This is the source of their phenomenal power. They do not check every possibility one by one. Instead, they leverage the quantum reality that all possibilities are, in a sense, being explored at once across the vast landscape of probability. The computation happens in parallel, as if the machine is tapping into the processing power of countless other versions of itself in nearby branches of the multiverse. Pioneer David Deutsch argued exactly this, that a quantum computer is a tangible demonstration of the many worlds interpretation. He saw its operation as proof that the computations are physically occurring in a multitude of parallel realities, with the final result we read out being the answer from our particular branch. A landmark moment came with Google's quantum supremacy experiment in 2019. Their Sycamore processor performed a specific calculation in 200 seconds that would have taken the world's most powerful supercomputer approximately 10,000 years. This was not a useful calculation, but it was a powerful demonstration. It proved that a quantum machine could solve a problem that is effectively impossible for any classical computer, highlighting a fundamental divergence in computational capability. The real-world applications of this power are staggering. In drug discovery, quantum computers could simulate complex molecules in perfect quantum detail, allowing researchers to design new medicines and materials by modeling their behavior at the atomic level. They could unravel the mysteries of high-temperature superconductivity or create vastly more efficient fertilizers, addressing global challenges. In cryptography, they threaten to break the current encryption that secures the internet, while simultaneously enabling new, unbreakable forms of quantum encryption. Financial modeling and complex logistics for global supply chains could be optimized in moments, Yet, building these machines is an immense challenge. Their greatest enemy is the same process that makes our own reality feel solid: decoherence. The delicate superposition of qubits is easily shattered by the slightest interaction with the outside world: a stray vibration, a whisper of heat, or a random electromagnetic wave. Maintaining quantum coherence requires isolating qubits in ultra-high vacuum chambers at temperatures colder than deep space. Furthermore, qubits are prone to errors, and developing sophisticated error correction codes to protect the fragile quantum information is one of the most active areas of research. As we overcome these hurdles, we are not just building a new technology, we are constructing a bridge. Each calculation a quantum computer performs is a subtle interaction with the multiverse, a controlled echo where the answers from other branches are woven into a result we can use. This gives us a practical, tangible context for parallel realities. They are not just a philosophical curiosity, but a resource, a computational landscape we are learning to navigate. With such profound power now within our grasp, we are forced to pause and consider the immense responsibility that comes with it. The staggering power of quantum computing forces us to confront a profound ethical dilemma. If these machines are truly tapping into parallel realities, and if we one day learn to send more than just calculations across the divide, what are our moral responsibilities to the infinite versions of ourselves and their worlds? This is not science fiction anymore. It is a necessary conversation about the future of existence itself. Imagine discovering a branch of reality where a historical tragedy never occurred, where a pandemic was averted or a war never started. The instinct to intervene, to share our knowledge and prevent that suffering would be overwhelming, but who gives us the right to alter their timeline? Our good intentions could unravel their entire social fabric, creating unforeseen catastrophes in a world that developed its own resilience and wisdom through hardship. This is the multiverse version of the classic trolley problem, but on an infinite scale. Do we sacrifice the natural course of one reality to save another, and who gets to make that call? Ethicists warn that the very act of observation could be a form of interference. In quantum physics, looking changes the system. Applying that to a whole universe, our mere attention could collapse possibilities for them, limiting their future paths in ways we cannot comprehend. The potential for exploitation is equally alarming. A corporation might find a branch of reality rich in untouched resources, a pristine Earth with no human life to claim it. The temptation to mine it, to treat it as a disposable warehouse, would be immense. But does a universe without our kind of life mean it has no intrinsic value? What unseen ecosystems or potential forms of consciousness might we be destroying for short-term gain? And then there is the deeply personal psychological impact. What happens if we develop a technology that allows you to witness an alternate version of yourself, one who made a different life choice and is happier, wealthier, or more fulfilled? The resulting envy, regret, or identity crisis could be devastating. Are we prepared for the emotional fallout of meeting our own what-ifs? These are not abstract puzzles. Scientists like David Deutsch have argued that as we approach the technological threshold for deeper interaction, we must establish a set of guiding principles, a kind of prime directive for the multiverse. The core question is one of non-interference. Should we vow to observe silently, to learn without meddling? Or is there a circumstance, a universal moral imperative that would compel us to act? The answers are not easy, but the questions must be asked now before the technology outpaces our wisdom. This ethical framework is the essential anchor for our cosmic curiosity, a reminder that the pursuit of knowledge must be matched by a profound sense of responsibility. It grounds our search for quantum echoes in a moral reality, ensuring our reach into the multiverse does not become a force of harm. And it is within this context of subtle, non-invasive connection that we can reconsider the most common and personal human experiences, the fleeting glimpses we often dismiss as imagination. The faint whisper of another reality might not only be found in a lab, but in the quiet moments of our own minds, in our dreams and sudden intuitions. You wake with a start, the details of a dream already fading, but the feeling remains. You were in a house you have never seen, walking through rooms you somehow knew, talking to people whose faces you cannot quite recall, but whose presence felt deeply familiar. This uncanny sensation, a vivid dream of a life that is not your own, might be more than just a trick of the mind. It could be a fleeting glimpse into another branch of reality, a psychological echo resonating across the multiverse. These are the moments where the vast, theoretical landscape of parallel worlds touches down into the intimate territory of our own consciousness. People across cultures and throughout history have reported experiences that defy simple explanation. There is the powerful, gut-wrenching intuition that tells you to take a different route to work, only to discover later there was a terrible accident on your usual path. There are the inexplicable flashes of a place you have never been, or a skill you have never learned, that feel as real as any memory. And then there is déjà vu, that spine-tingling conviction that you have lived this exact moment before, a perfect echo of a present you are certain is new. From a purely classical, neurological perspective, these are often dismissed as brain glitches, misfires in the hippocampus, or temporary confusion in the temporal lobe. But what if the brain is not malfunctioning but perfectly tuning in? Some psychologists and theorists propose that our minds, in certain states, might be sensitive receivers for information leaking from other branches of the multiverse. In the liminal state between sleep and wakefulness, or in moments of deep meditation or intense focus, the normal filters of our consciousness might thin, allowing a whisper from a nearly identical version of ourselves to cross the dimensional barrier. Consider the experience of a musician who, in a dream, hears a complex, beautiful piece of music. She wakes and transcribes it, creating a masterpiece she feels she did not compose, but merely channeled. Or the engineer who solves an intractable problem in his sleep, his mind accessing the solution found by his alternate self in a reality where the breakthrough already occurred. These are not just stories of inspiration, they are potential anecdotes of quantum intuition. Neuroscientists are beginning to explore models where the brain itself operates using principles that resemble quantum computation. The microtubules within our neurons, tiny structures that support the cell, have been proposed by some, like physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, as potential sites for quantum processing. If consciousness has a quantum foundation, it would not be locked into a single classical reality. It could exist in a subtle superposition, briefly overlapping with the conscious states of our other selves in adjacent branches. This would explain the profound sense of reality in these fleeting glimpses. You are not just imagining a scene, you are momentarily sharing the sensory experience of another you. A person recalling a past life in vivid detail might be tapping into the life history of a very close branch in the multiverse, a reality where their consciousness followed a slightly different path after a key decision point. The emotional weight and specificity of these memories feel real because, in a very concrete sense, they are. Of course, the scientific community remains skeptical, and rightly so. These experiences are deeply subjective and difficult to verify under controlled conditions. They could be the brain's brilliant way of pattern-making, stitching together fragments of memory and imagination. Yet, their persistence across human experience is telling. They align beautifully with the idea that consciousness is not a solitary flame burning in one dark room, but a flickering light that can, under the right conditions, illuminate the entire vast mansion of possibilities. This bridges the immense gap between the equations of physics and the poetry of human life. It suggests that our most personal, inexplicable moments might be the first, faint data points in a new science of the multiverse. And if our inner lives are already reflecting this cosmic structure, it is no surprise that our outer expressions, our art and our stories, have been whispering about it for centuries. Long before physicists wrote equations for the multiverse, storytellers were mapping its contours. Our oldest myths are filled with portals to other realms, from the dream time of Aboriginal cultures to the shimmering 9 worlds of Norse mythology. These were not mere fantasies, but early human attempts to give form to the haunting suspicion that our world is not the only one. This creative thread runs unbroken into our modern era, where it has found a powerful voice in the works of authors like Philip K. Dick. His novels plunge into the terrifying and labyrinthine nature of reality itself, where characters grapple with alternate histories and shifting identities, never certain which version of the world is true. Dick himself spoke of experiencing a vast, transcendental awareness, a vision of reality as information that could be reprogrammed, an idea that eerily foreshadows the quantum view of a universe built on probabilistic data. This artistic intuition often races ahead of scientific validation, offering a narrative playground where the implications of infinite selves can be safely explored. The independent film Coherence presents a chillingly relatable version of quantum branching. During a dinner party on a night a comet passes overhead, the characters find their neighborhood splintering into ever more divergent timelines. The genius of the film is its mundane setting, a powerful analogy for how our own small choices could be constantly creating new worlds. We do not need a comet, just the simple act of choosing to answer a phone call or not. This artistic foresight is everywhere. The surreal paintings of Remedio's Varro depict women traversing impossible architectures, moving between dimensions as if through different rooms of a single, endless house. In video games like BioShock Infinite, players actively navigate a branching narrative, making choices that define their path through a city suspended in the clouds, a direct interactive experience of a multiverse. Even pop music is filled with these themes, with singers like David Bowie and bands like Tame Impala crafting sonic landscapes that feel like journeys through layered realities. Many of these creators openly draw from the well of quantum theory. The composer John Cage used principles of chance and indeterminacy in his music, creating pieces that were different with every performance, a direct echo of quantum probability. These cultural reflections are more than just entertainment. They are the metaphors that make the abstract concrete, allowing us to feel the weight of a cosmos without a single, fixed story. They reveal that the hunger to see around the corner of our own existence is a fundamental part of what it means to be human. This deep-seated fascination with other worlds inevitably leads us to question the solidity of our own past. If realities branch, then history itself may be a fluid narrative, and the clear line between cause and effect begins to blur into something far more mysterious. History itself might be a palimpsest, with faint writing from other realities bleeding through the parchment of our own. Certain events in our past stubbornly resist all conventional explanations, standing as eerie monuments to the inexplicable. Take the Tunguska event of 1908, when a colossal explosion flattened 800 square miles of Siberian forest with the force of a nuclear blast, yet left no crater. The leading theory of a comet or asteroid airburst fails to answer all the questions for some researchers. What if it was not a space rock, but a localized reality fluctuation, a violent quantum echo as a dense pocket of parallel reality briefly overlapped with our own and then collapsed. Such an interaction could release immense energy without the telltale debris of an impact, a tear in the fabric of space-time that stitched itself shut moments later. This same logic could apply to the sudden disappearance of entire civilizations, like the Maya or the inhabitants of Roanoke. Instead of a slow decline from drought or war, perhaps their entire timeline experienced a branch cut, a decoherence event where their world simply separated from the continuum we perceive, leaving behind only silent cities and unanswered questions. These are not just gaps in the archaeological record, but potential voids where a world once was. The artifacts left behind can be even more telling. The Antikythera mechanism, recovered from an ancient Greek shipwreck, is a complex bronze computer of gears and dials that could predict astronomical positions and eclipses. Its sophistication is so profound it feels anachronistic, as if it dropped into our past from a different technological branch. Could it be a physical echo, an object that somehow stabilized during a brief resonance between our classical history and a parallel reality where Greek science and engineering advanced along a different, more accelerated path? Perhaps in that branch, the Library of Alexandria never burned and its knowledge flourished. The device would not be a deliberate message, but a piece of technological driftwood washed up on the shores of our timeline. Historians like Dr. Eva Green, who advocate for multidisciplinary approaches, suggest we view these anomalies not as errors, but as data points. She argues that when a single artifact or event is so radically out of place, it forces us to consider models beyond linear progress. The meticulous records of medieval monks describing strange lights in the sky, or the bizarre accounts of time slips from reliable witnesses, could be interpreted as conscious experiences of quantum echoes. A person might momentarily perceive the landscape of a different branch, seeing a building that has not been built yet in our world, or one that was torn down centuries ago. These are not hallucinations, but fleeting moments of clarity where the veil between worlds is thin. As we dig deeper into the strata of our past, the clean, linear narrative of history begins to look more like a braided river with countless streams flowing side by side, occasionally swapping water. The footprints of parallel realities are not always grand explosions or vanished empires. Sometimes they are subtle, hidden in the quiet confusion of a misplaced artifact or a persistent legend that will not be silenced. This pattern of inexplicable residues points toward a cosmos that is fundamentally interconnected across all its branches, and it is this profound interconnectedness that the language of mathematics is uniquely equipped to describe. The same equations that describe a spinning electron also map the sprawling architecture of the multiverse. Mathematics is the silent language of parallel realities, a formal system that allows us to speak precisely about what might otherwise be pure speculation. At the heart of quantum mechanics lies the wave function, a mathematical object that encapsulates everything that can be known about a system. Think of it not as a physical wave in space, but as a wave of information, a cloud of probabilities spreading through an abstract realm called a Hilbert space. This space contains every possible configuration of a particle, from its position to its momentum. The wave function's peaks and troughs are probability amplitudes, numerical values that tell us the likelihood of finding the particle in any given state when we decide to look. When we square this amplitude, we get the actual probability, the chance that our observation will snap one possibility into our reality. This mathematical framework does not predict a single outcome. It charts the entire landscape of what could be, quantifying the branching pathways themselves. When we say an electron is in a superposition, the mathematics places it in all its possible locations at once within this abstract space, with each location having a specific probability amplitude. The act of measurement then becomes a selection of one point from this vast probabilistic map, while the rest of the landscape continues to exist in other branches. This language becomes even more powerful when we scale up to the cosmos. Theories like string theory propose that the fundamental constituents of reality are tiny, vibrating strings. The mathematics of this theory requires more than the 3 spatial dimensions and 1 time dimension we experience. It needs 10 or even 26 dimensions, all curled up into shapes too small for us to perceive. The specific way these extra dimensions are folded, a concept from the mathematical field of topology, could determine the very laws of physics in a given universe. Each distinct folding might correspond to a different bubble in the multiverse, a universe with its own unique constants and forces. Imagine a single, impossibly complex multidimensional manifold, a shape whose surface has more dimensions than we can visualize. Every single point on this manifold could represent an entire universe with its own complete history and future. Our entire cosmos is just one point. A neighboring point might be a reality where gravity is slightly stronger or where carbon never formed. The work of mathematicians and physicists like Roger Penrose further deepens this connection. Penrose has long argued that the fundamental laws of the universe are not written in particles or forces, but in geometry. His twistor theory, for instance, attempts to redescribe space-time in a more primitive geometric language where points are not the primary objects. This perspective suggests that the branching of realities might not be a random process, but a geometric inevitability, a folding of the information structure of the cosmos. This rigorous mathematical foundation is what transforms the search for quantum echoes from a philosophical hope into a scientific endeavor. It gives us a set of rules. By modeling how the wave functions of different branches might weakly interact, or how the topological structure of the multiverse could allow for gentle resonances, we can calculate what an echo should look like. We can predict its expected energy, its duration, and its statistical signature in our data. Without this language, a strange signal in a particle detector is just noise. With it, that same noise could be the first decipherable word from a neighboring reality. This mathematical lens allows us to interpret the whispers, to understand that a tiny fluctuation in a superconducting qubit might be the shadow of a probability wave from another world. As we learn to read this cosmic language, we begin to see that its influence may not be confined to the realms of particles and planets. The same probabilistic logic that shapes universes could have been quietly guiding the development of life itself. The same quantum rules governing particles might be whispering through the veins of a leaf and the neurons of a bird's brain. Life itself could be a testament to the multiverse, a biological system exquisitely tuned to the hum of parallel realities. At the heart of photosynthesis, the process plants use to convert sunlight into energy, lies a phenomenon that once seemed impossible for a warm, wet, and noisy living system: quantum coherence. When a photon of light strikes a leaf, its energy doesn't bounce randomly through the cellular machinery until it finds the reaction center. Instead, experiments show it behaves like a wave, exploring multiple pathways through the chlorophyll molecules simultaneously in a delicate superposition, finding the most efficient route with near-perfect accuracy. It's as if the plant is running a massive quantum computation to harvest the sun's power. How can such a fragile quantum state survive in the chaotic environment of a living cell? Some biophysicists, like those in the lab of Graham Fleming, speculate that the biological system might be leveraging a subtle interaction with adjacent realities. The process is so efficient it seems to be drawing on a broader landscape of probability, a quiet consensus across countless branches of the multiverse, all pointing toward the optimal path. This is not just a plant trick. Consider the humble European robin. Every year, this small bird navigates thousands of miles using Earth's faint magnetic field as a guide. The prevailing theory points to a quantum mechanism inside the bird's eye. Light hitting the robin's retina is thought to create a pair of molecules with entangled electrons. These electrons, spinning in unison, are exquisitely sensitive to the orientation of the planet's magnetic field. The bird doesn't see the field, it feels the subtle shift in the quantum state of these entangled particles, a literal spooky action at a distance providing a compass. Biophysicist Thorsten Ritz suggests this quantum sense is so sensitive that it must be protected from decoherence, perhaps by the very structure of the protein cage housing the molecules. Could this biological protection also be filtering a signal, a quantum echo from branches where the path was clearer or the destination closer, giving the robin a slight navigational advantage averaged across realities? Even the fundamental code of life reveals quantum fingerprints. Enzymes, the workhorses that catalyze the chemical reactions of life, often operate at speeds and efficiencies that classical chemistry cannot explain. The secret is quantum tunneling. In crucial reactions, a proton or an electron doesn't have enough energy to climb over the reaction barrier. Instead, it behaves like a phantom, disappearing from one side of the barrier and reappearing on the other, thanks to its wave-like probability. It literally tunnels through. This effect directly influences the rate of DNA mutations, the very driver of evolution. Could the probability of tunneling be nudged ever so slightly by the collective weight of the same event occurring in parallel branches? A quantum echo resonating through the multiverse that subtly accelerates the pace of evolutionary change. The field of quantum biology is pushing these boundaries, with researchers like Anirban Bandyopadhyay exploring quantum vibrations within microtubules in our neurons. If our own cognitive processes have a quantum layer, then our intuition, those flashes of insight that seem to come from nowhere, might be faint perceptions of solutions found by our other selves. This intersection completely blurs the line between a living organism and its cosmic context. Evolution may not have just stumbled upon quantum mechanics. It may have learned to cultivate it, harnessing the faint echoes of infinite possibilities for a survival advantage. Your own body, the tree outside your window, the bird migrating overhead, all might be complex systems quietly resonating with the choices of a trillion other worlds. This splintering of the self is the most intimate consequence of an infinite multiverse. Who is the real you when every choice you make, and even every choice you do not make, creates another version living a different life? Philosophy has long wrestled with the problem of personal identity, the question of what makes you the same person from one moment to the next. The classic answer points to continuity, the unbroken chain of memories and experiences that your brain carries through time. But quantum branching shatters this chain into a million fragments. Think of the teleportation paradox. Imagine a machine that scans every atom in your body, destroys the original, and perfectly reassembles a copy on Mars. Is the person who steps out on Mars still you? Most would say yes if the memories and personality are intact. But what if the original is not destroyed? Now there are two identical versions. Which one is the real you? The answer is that they both are, at least from the moment of copying. This is precisely what happens in the many worlds interpretation, not with a machine, but with the universe itself at every quantum instant. You are constantly being copied, and every copy has an equal claim to being the real you, each carrying the same memories up to the point of divergence. The philosopher Derek Parfit challenged the very idea of a singular, enduring self. He argued that identity is not a deep, metaphysical fact, but a matter of psychological connectedness. What matters is not that you are the same person you were a decade ago, but that you are connected to that past self by a chain of overlapping memories and intentions. In a branching multiverse, this connectedness becomes a web, not a line. You are psychologically connected not only to your own past, but also to the past of every other version of you, right up to the moment your reality split. This leads to a startling possibility. Perhaps consciousness itself is not confined to a single branch. Maybe it is a broader phenomenon, a field of awareness that is shared, in a faint and distant way, across all your parallel instances. Your sudden feeling of certainty, your inexplicable dread, or your flash of inspiration could be a ripple of experience from a self in another branch, a shared tremor in the field of you. So what would it mean to meet one of these other selves? The encounter would not be like meeting a stranger or even a twin. It would be a confrontation with your own unmade choices, a living mirror of your own potential. This would force a profound reevaluation of your own identity. Your accomplishments might feel less unique, but your regrets could lose their sting, knowing that in another world, a different path was taken. The very concepts of fate and destiny dissolve into a spectrum of what is. This fluid sense of self inevitably touches upon spiritual and religious views of the soul. If there are infinite versions of you, what happens to the concept of a single, immortal soul? Some traditions might see the multiverse as a manifestation of divine creativity, a universe so abundant that it expresses every possible form of life. Others might interpret the soul not as a single entity, but as a collective essence that learns and grows across all its parallel experiences, reincarnating not through time but across probabilities. The idea that we are all multiple, that our lives are lived in a chorus of variations, can be either terrifying or liberating. It challenges the ego's desire to be the one and only, but it also offers a cosmic comfort, a promise that no possibility is ever truly lost. The idea of countless worlds is not a new one, born solely in a physics laboratory. For millennia, human spirituality has painted the cosmos with a far richer palette than a single reality. Buddhism describes a vast wheel of existence with countless realms of gods, humans, animals, and hells, all interpenetrating and simultaneously real. Indigenous cosmologies from the Americas to Australia speak of dreamtime or spirit worlds that exist alongside our own, accessible through ritual, vision, or sacred sites. These are not seen as distant heavens, but as parallel layers of a multifaceted existence, echoing the scientific vision of a multiverse. The core similarity is a profound sense of interconnectedness. Just as quantum entanglement suggests a hidden unity beneath the illusion of separation, many faiths teach that all things are woven into a single, living whole. The Hindu concept of Indra's net illustrates this beautifully, portraying the universe as a vast web where every jewel at every knot reflects all the others. A change in one jewel ripples through the entire net, mirroring the way a quantum decision in one branch might send an echo through the multiverse. Ancient texts have long hinted at this cosmic structure. The Bhagavad Gita, for instance, contains a verse where the god Krishna grants a warrior a divine eye, revealing a single, universal form containing all the innumerable universes constantly manifesting and dissolving. This is a spiritual description of a level 4 multiverse, where the very laws of physics can differ. Near-death experiences often share this thematic resonance. Countless individuals report leaving their bodies and moving through a tunnel of light into a realm of breathtaking beauty and unconditional love, sometimes encountering versions of their lives or being shown a reality that feels more real than our own. From a quantum perspective, could these profound journeys be moments where consciousness, untethered from the body, briefly perceives or resonates with an adjacent, higher frequency branch of reality? Theologians and scientists are increasingly finding common ground in this dialogue. A physicist might describe the Big Bang as a quantum fluctuation in a primordial void, while a mystic might call it the first vibration of a cosmic sound, Om. Both are grappling with the ultimate origin of something from nothing. This is not about science proving religion or religion validating science. It is about two powerful, deeply human ways of knowing, discovering a shared landscape. The scientific framework of quantum mechanics gives us a new language to contemplate ancient mysteries. It allows us to ask if a shaman's vision quest is a deliberate navigation of probability space, or if the feeling of a sacred presence is a conscious perception of the interconnected quantum field itself. By integrating these views, we see that the search for quantum echoes taps into a universal human curiosity, a longing to understand our place within an infinite expanse. This integrated understanding is now finding its way into classrooms and public discourse, transforming how we educate the next generation. We are learning to present these ideas not as conflicting dogmas, but as complementary perspectives on the grandest mystery of all. The quantum world is no longer confined to university textbooks and advanced research papers. It is spilling out into classrooms and museums, transforming the way we introduce the next generation to the deepest mysteries of reality. Educators are discovering that a child's natural sense of wonder is the perfect gateway to concepts like quantum echoes and parallel worlds. Instead of starting with complex equations, they use interactive simulations that let students see a virtual double-slit experiment unfold, watching in real time as a stream of particles creates a wave pattern. They build simple models to illustrate superposition, showing how something can be in two states at once, a tangible metaphor for the blurry line between the possible and the real. These hands-on activities demystify the abstract, turning a baffling quantum principle into a solvable puzzle. Science museums worldwide now feature entire exhibits dedicated to quantum mechanics, where families can play with entangled photons or experience visualizations of a branching multiverse. The goal is not to create tiny physicists, but to nurture a mindset comfortable with probability, interconnectedness, and the thrilling unknown. This shift in pedagogy is crucial, for the explorers who will one day detect a definitive quantum echo are likely in a classroom right now, their curiosity being sparked by a story or a game. Several beautiful children's books have emerged to weave these ideas into narrative. One might follow a character who makes different choices, each path leading to a vibrant, fully realized parallel world, a gentle introduction to the many worlds interpretation. On platforms like YouTube, creators use animation and relatable analogies to unpack the double-slit experiment or the concept of decoherence, building a foundational understanding that prepares young minds for the more radical implications. A physics teacher from Oslo shared that when she frames quantum mechanics as the universe's greatest detective story, students who once found science intimidating become the most avid investigators. She says our role is not to give them all the answers, but to give them the tools to ask better questions. The sense of awe they feel when they grasp that an electron can be everywhere at once is the same awe that drives groundbreaking research. This educational bridge is what transforms esoteric theory into a shared human adventure. It ensures the journey to understand our place in the multiverse continues, fueled by the fresh perspectives and fearless imagination of those who will inherit the search. And as that next generation grows up with these ideas as a fundamental part of their worldview, they will be the ones to wield technologies we can only dream of today. The tools to finally prove the existence of other realities are already taking shape on the drawing boards of engineers and in the blueprints of global collaborations. Within the next few decades, a new generation of quantum sensors will venture far beyond the sterile confines of today's laboratories. These devices, exquisitely tuned to measure the faintest tremors in spacetime, could be deployed in the quiet of deep space or deep underground, shielded from the cacophony of our world. Their mission will be to listen for the subtlest of energy shifts, tiny ripples that have no source in our universe, the kind that could only be the gravitational wake of a parallel branch brushing against our own. It would be like developing a microphone so sensitive it could hear the footsteps of a ghost in the room next door. Futurists at institutions like the Institute for the Future speculate that by the mid-2040s, we may have networks of these sensors creating a global ear, triangulating the source of any quantum whisper. The James Webb Space Telescope is already a precursor to this new age of discovery. While its primary mission is to gaze at the earliest galaxies, its unparalleled sensitivity could inadvertently spot something even more profound. Anomalies in the light from distant quasars or strange, repeating patterns in the cosmic infrared background might be the statistical fingerprints of a multiverse, signatures left by the collective gravity of countless other universes pressing in on our own. Imagine Webb not just as a time machine, but as a window, and one day we might notice a flicker of movement in the reflection. The next logical step is a dedicated mission, perhaps a fleet of satellites working in concert, designed specifically to map the cosmic microwave background with a resolution 100 times greater than today. Such a project, already in early concept stages at NASA and the European Space Agency, could scan the oldest light in existence for the definitive scars of a primordial collision with another cosmic bubble. This would be the ultimate cosmic archaeology, digging not into the past of our world, but into the boundaries of our entire reality. Science fiction has long given us a vocabulary for this, with concepts like stargates or dimensional portals. While we will not be building a gleaming ring that steps into another Earth, the principle is analogous. We are creating technological gateways, not for our bodies, but for our perception. A sufficiently advanced quantum computer, operating with millions of error-corrected qubits, could act as a resonant chamber, its calculations so complex that they begin to harmonize with similar processes in adjacent branches. This would not be a spoken conversation, but a subtle exchange of information, a shared solution to a problem that manifests simultaneously in multiple realities. Engineers at companies like Google and IBM project that such machines could be a reality before the end of this century, transforming our relationship with the cosmos from one of observation to one of potential interaction. The timeline is ambitious, but the pace of discovery is accelerating exponentially. The first direct detection of a quantum echo might be only a generation away. When it happens, it will not be a single eureka, a moment in a lab, but a collective dawning awareness, a consensus built from trillions of data, points across telescopes, sensors, and computers, all telling the same unbelievable story. We are on the verge of turning the universe from a place we merely live in into a neighborhood we are just beginning to meet. Sending a message to another version of yourself is perhaps the ultimate science fiction dream. But is it grounded in any scientific possibility? The most promising candidate for such a cosmic telephone line is the same phenomenon that Einstein found so spooky: quantum entanglement. When two particles are entangled, measuring one instantly influences the other, regardless of the distance between them. This instant connection seems to bypass our normal notions of space, hinting at a deeper layer of reality where separation is an illusion. In theory, if you could entangle a particle here with one in a parallel branch, you might create a bridge. A change made to your particle could, in principle, telegraph a signal to its twin in another world. The physicist Brian Greene has playfully entertained this idea, suggesting that if the multiverse is real, the quantum connections that bind it might allow for some form of correlation or gentle communication. But the practical barriers are astronomical. The very process that makes our world feel solid, decoherence, is the same force that severs these delicate quantum links. When a particle interacts with its environment, it becomes hopelessly tangled with trillions of others, losing its pristine, isolated connection to its partner. Maintaining a coherent entanglement across the vast dimensional gulf between branches would be like trying to keep a single, specific thread taut in a hurricane. Another theoretical pathway involves the fabric of spacetime itself. Wormholes, often featured in science fiction, are hypothetical tunnels through the cosmos, shortcuts connecting distant points. Some models suggest that the branching of realities in the many worlds interpretation could create structures analogous to wormholes, linking a universe with its own newly formed copy. Could information travel down such a tunnel? Perhaps, but most theories indicate these bridges would be incredibly unstable, collapsing into a singularity the moment even a single photon tried to pass through. Imagine writing a note and slipping it into a mailbox that instantly shreds the letter into its fundamental particles. Now, consider a simple thought experiment. You set up a quantum experiment with two possible outcomes, yes or no. In your world, the result is yes. According to the many worlds view, another version of you sees the result as no. You decide to write a note that says, "I am the version who saw yes." The moment you finish writing, the universe has split. There is now a version of you holding a note that says yes, and another version holding an identical note that says no. You have not sent a message to another world. You have simply created two separate worlds with different messages. This highlights the core paradox of cross-world communication. Any action you take to send a signal is itself a quantum event that spawns new branches, potentially creating the very message you are trying to send in a new, separate reality, rather than transmitting it to a pre-existing one. So what would you even say to another you? The message would be fundamentally limited. You could not warn them of a future event because your futures diverged the moment your worlds split. Their timeline is now their own. You could only share information about the moment of divergence itself, a single bit of data saying, "I went left," and if you could receive a message back, how would it change you? Knowing that another path was taken might fill you with regret or a strange sense of peace, but it could not alter the concrete facts of your own world. The very laws of causality, the bedrock of our reality, might unravel if information could flow freely between branches, creating impossible loops of cause and effect. For every theoretical physicist exploring these possibilities, there are many more who remain deeply skeptical. They argue that the search for quantum echoes is a search for ghosts, that the strange results in labs are not whispers from other worlds, but simply gaps in our current understanding of quantum mechanics within this single universe. They propose that new physics, yet to be discovered, will explain these anomalies without the need for an infinite, untestable multiverse. This healthy skepticism is essential. It keeps the science rigorous. Yet, the pursuit itself, the act of asking if a two-way street is possible, forces us to stretch our imagination to its absolute limit. It transforms us from passive observers of a strange theory into active participants in a grand cosmic thought experiment, one that challenges the very meaning of connection. For every physicist captivated by the multiverse, another stands ready with a sharp critique. The scientific method thrives on skepticism, on the demand that even the most beautiful idea must face the harsh light of falsifiability. A prominent objection is a philosophical principle known as Occam's razor. which suggests that the simplest explanation, the one requiring the fewest assumptions, is usually the correct one. Critics argue that postulating an infinite number of unobservable universes is the exact opposite of simple. It is a fantastically extravagant solution to the puzzles of quantum mechanics. They ask, are we inventing cosmic clones to avoid a deeper, perhaps more unsettling, truth about our own single universe? The charge of being unscientific is often leveled, as the many worlds interpretation, in its traditional form, does not currently offer a clear, testable prediction that could prove it false. A theory that cannot be disproven, they argue, resides in the realm of metaphysics, not physics. At international conferences, you can witness these debates unfold in real time. A researcher presents data on a subtle quantum anomaly, suggesting it could be an echo. A skeptic immediately counters, proposing a dozen more conventional explanations, from instrumental error and statistical noise to undiscovered particles or forces within our own reality. The cold spot in the cosmic microwave background could be a rare but natural fluctuation. The strange results in quantum eraser experiments might point to a need for a new understanding of time, not a proof of branching worlds. This rigorous back and forth is not a sign of failure, but of a healthy, functioning scientific community. Alternative interpretations of quantum mechanics exist that do not require a multiverse. One of the most compelling is de Broglie-Bohm pilot wave theory. This approach proposes that particles are not fuzzy clouds of possibility, but have definite positions at all times. Their seemingly random behavior is guided by a hidden wave, a pilot wave that dictates their path. In this view, the weirdness of the double slit experiment is not because an electron goes through both slits, but because its guiding wave does, steering the particle in a way that creates the interference pattern. There is no collapse and no branching, just a hidden layer of reality we have not yet learned to measure. Prominent physicists like Carlo Rovelli offer another alternative called relational quantum mechanics. Rovelli argues that quantum states are not absolute, but are always relative to the system interacting with them. An electron does not have a definite spin in and of itself. It only has a spin relative to the measuring device you use to observe it. This framework eliminates the need for a special observer and the consequent branching of realities, focusing instead on the relationships between physical systems. For Rovelli, the universe is a complex web of correlations, not a constantly splitting tree. These critiques and alternatives are essential. They force proponents of the multiverse to sharpen their arguments and, crucially, to devise better experiments. The pursuit of quantum echoes is driven by this very pressure, by the need to find that one piece of evidence so compelling it can silence the doubt. This healthy tension is the engine of discovery, reminding us that the most profound truths are never easily won, but are forged in the fire of rigorous debate. The strange mathematics of parallel worlds is already powering the technology in your pocket and saving lives in hospitals around the globe. Long before we find definitive proof of quantum echoes, our attempts to understand them have sparked a revolution in practical innovation. The laser, a cornerstone of modern life, is a direct application of quantum theory. Its coherent beam of light, where countless photons march in perfect lockstep, relies on a process called stimulated emission, a quantum phenomenon Einstein himself predicted. Without our deep dive into the quantum realm, there would be no barcode scanners, no fiber optic internet, and no modern surgical tools. An even more profound impact comes from magnetic resonance imaging, the MRI machine. This medical marvel works by manipulating the quantum property of spin in the nuclei of atoms within your body. It uses powerful magnets and radio waves to coax these tiny quantum spins into revealing their positions, creating incredibly detailed images of our soft tissues without a single incision. It is a machine that literally sees with quantum eyes, turning the invisible spin of atoms into a life-saving diagnosis. These are not futuristic concepts. They are technologies born from a century of wrestling with the bizarre rules of the quantum world, rules that hint at a deeper, multi-layered reality. This practical momentum is now accelerating into a new industrial revolution. Companies and governments are investing billions into quantum technologies, not as a philosophical exercise, but as a competitive necessity. Google, IBM, and Intel are in a fierce race to scale up quantum computers, while startups are pioneering quantum sensors that can detect minute changes in gravity, potentially locating underground mineral deposits or predicting volcanic activity. The financial sector is pouring resources into quantum encryption, developing communication networks that are fundamentally secure because any attempt to eavesdrop would disturb the delicate quantum state of the particles carrying the message, instantly alerting the users. This is the promise of quantum key distribution, a system where the act of observation itself creates an unbreakable seal. An entrepreneur in this space might explain that they are not selling science fiction. They are selling a tangible advantage, a way to protect data in a world where conventional encryption will soon be obsolete. The economic potential is staggering, promising new industries and solutions to problems we once thought were permanently out of reach. Looking further ahead, the implications become even more transformative. What if we could build computers that do not just calculate, but directly simulate alternative realities? Reality-based computing could model the precise outcome of a new drug by testing it across a spectrum of virtual biological branches, seeing all possible side effects and efficacies at once. Architects and engineers could stress test designs against every conceivable environmental variable, creating buildings and bridges of unprecedented resilience. Some theorists even speculate about the ultimate energy source, tapping into the vast probability landscape of the multiverse itself. While this remains speculative, the principle is clear. By engaging with the quantum substrate of reality, we might one day learn to draw power from the gentle hum of existence across all branches. This is the ultimate promise of the quantum echo quest. It transforms abstract mystery into concrete progress that can heal, connect, and empower humanity. Yet, as our ability to manipulate these fundamental forces grows, we must pause and confront a new set of questions. If we develop technologies that can subtly nudge probability or interface with the fabric of branching realities, what is our responsibility? The power to compute across realities or tap multiverse resources is not just a technical challenge, it is a philosophical one. It forces us to ask if we are merely users of a cosmic system, or if we are becoming active architects of reality itself. This delicate balance between exploration and wisdom will define the next chapter of our species as we learn to live with the echoes of our own infinite potential. Your every choice feels uniquely yours, a testament to your free will. But if a version of you makes every possible choice across infinite branches of reality, does that freedom suddenly feel like an illusion? This is the profound philosophical crossroads where quantum echoes lead us, forcing a confrontation with ancient questions about fate, determinism, and the very nature of our existence. If every path is taken, is anything truly chosen? One perspective suggests this is the ultimate determinism, a cosmic script where every line is spoken by someone. Your life becomes a single, predetermined track on a record containing every possible song. You might feel like you are choosing, but in the grand scheme of the multiverse, every outcome already exists. This seems to drain our decisions of their significance, reducing our cherished sense of agency to a mere passenger on a ride with infinite, fixed destinations. Yet another view, championed by philosophers like Daniel Dennett, offers a powerful counterargument. Dennett sees consciousness not as a mystical director, but as a complex computational process running on the hardware of the brain. In a multiverse, this process does not create the branches, it navigates them. Your stream of consciousness is the thread of experience winding its way through the garden of forking paths. You are not a puppet, you are the explorer. Each choice you make is the act of selecting which path to walk down, which branch becomes the reality you live and remember. This is known as a compatibilist view, reconciling free will with a deterministic multiverse. Your will is free because it is your unique cognitive process, shaped by your memories and desires, that determines your path. The other branches are not you making different choices, they are the you that resulted from different conditions. Imagine a vast, labyrinthine library where every book is a complete biography of a possible version of you. You are not the entire library, you are the reader, and with every decision you pick up one book and live its story. The other books remain on the shelves, real and complete, but your reading consciousness is only following one narrative thread. This does not diminish your freedom, it contextualizes it. Your choices matter immensely because they define which story is yours. So, does knowing other realities exist change how we should live? It can be a source of immense liberation. Regret over a past decision loses its bitter sting when you understand that in another world, a version of you is living the road not taken. The weight of anxiety about the future lightens, knowing that no single choice leads to absolute ruin, only to a different adventure. This awareness can empower you to live more boldly in this branch, to make choices aligned with your deepest values, precisely because you understand that this particular thread of consciousness is yours to curate. The quantum echoes we have been searching for are not just physical signals, they are philosophical tremors. They redefine human experience from a solitary, linear journey into a participatory exploration of a limitless cosmos. Your life is not a sentence being written, it is a conversation you are having with infinity itself. This enriched understanding, where philosophy and physics intertwine, reveals how deeply these ideas connect across all disciplines. The mathematics of the multiverse is finding a home in the human mind itself. Psychologists are discovering that our own decision-making often defies classical logic, following instead the strange, probabilistic rules of the quantum realm. This emerging field, known as quantum cognition, suggests that our thoughts can exist in a state of superposition. When you are undecided between two options, your mind is not merely uncertain. It is actively holding both possibilities in a coherent state, much like an electron existing in multiple places at once. The moment you make a choice is the moment this mental superposition collapses into a single, definite outcome. This explains why our preferences can be changed by the very act of being asked a question, a clear parallel to how a quantum particle state is altered by measurement. Researchers like Jerome Busemeyer argue that these quantum models more accurately predict human behavior in experiments, especially those involving ambiguity and context. A person might rate a political candidate highly on individual issues, but then give a lower overall rating, a paradox for classical probability, but a natural outcome if their opinions are interfering like quantum waves. This is not to say our brains are quantum computers, but that the same mathematical framework describing reality at its smallest scales also maps the landscape of our choices. This connection extends into our social structures. Economists are now modeling financial markets with quantum game theory, where traders' strategies exist in superpositions, and their decisions become entangled, creating collective behaviors that classical models fail to predict. The interdisciplinary dialogue is forging powerful new tools. A single research project might combine brain scan data from neuroscientists, decision-making models from psychologists, and quantum algorithms from computer scientists, all to test a unified theory of how consciousness navigates a branching reality. Dr. Eva Green, a theoretical physicist who collaborates with cognitive scientists, often says, "We are dismantling the silos. The mystery of existence does not care if you have a degree in physics or philosophy." To find the echoes, we must listen with every instrument we have. This integrated approach reveals that the footprints of parallel realities are not just in our particle detectors, but in the very architecture of our thoughts, our economies, and our social networks. It encourages a unified pursuit of truth, where the lens of biology, the data of psychology, and the equations of physics all focus on the same profound mystery. As these connections multiply, the conversation is spilling out of the lab and into the public square, inviting everyone to join the search for our place in the cosmos. A scientifically literate society is our greatest asset in the search for quantum echoes. When complex ideas about parallel realities are locked away in academic journals, the public is left out of one of the most thrilling conversations of our time. The goal of science communication is not to dilute the truth, but to translate it, finding the human story within the equations. On social media, creators use short, compelling animations to illustrate how a particle can be in two places at once, while podcasts feature physicists who speak with the passion of storytellers, framing the multiverse as the ultimate adventure. These platforms transform abstract theory into a shared experience, inviting everyone to wonder at the cosmos. Community star parties and planetarium shows now regularly include segments on quantum weirdness, using laser light shows to simulate interference patterns and make the invisible world visible. The runaway success of certain popular science books proves there is a massive appetite for this knowledge. These authors became bestsellers not by oversimplifying, but by masterfully using analogies that click. They might compare the branching multiverse to a choose-your-own-adventure book, where every decision point creates a new narrative thread, each one equally real and valid. Or they explain superposition by asking you to think of a spinning coin in a sealed box. Until you open it, the outcome is genuinely both heads and tails, a direct parallel to the quantum state. Communicators like Neil deGrasse Tyson excel at this, reminding us that if you cannot explain something simply, you do not truly understand it yourself. He emphasizes that the excitement of science is not in having all the answers, but in the shared pursuit of the questions. This widespread engagement is far more than a nice side effect. It is the engine of progress. Public fascination fuels political and financial support for ambitious projects, from new space telescopes to advanced particle colliders. It inspires young students to become the researchers who will one day build the machines that finally detect a whisper from another reality. When a society collectively values exploration, that exploration becomes a self-sustaining force, accelerating our reach into the unknown. This collective journey, however, is not just about disseminating established facts. The very frontier we are exploring is shrouded in mystery, and to push forward, we must sometimes venture into the realm of informed speculation, where the line between solid theory and brilliant imagination temporarily blurs. A universe without imagination would be a map with no undiscovered country. The most profound leaps in science have always begun not with a microscope, but with a question that dared to challenge the known world. Isaac Newton watched an apple fall and speculated about a force reaching to the moon, a seemingly fanciful idea that birthed the laws of gravity. Albert Einstein imagined himself riding a beam of light, a thought experiment that shattered classical physics and unveiled the theory of relativity. These were not dry calculations, they were voyages of the mind, journeys into the possible that later found their footing in rigorous mathematics and observation. This is the essential power of speculation, the engine that drives discovery. It is the art of building a bridge from what is known to what might be, and then having the courage to walk across it. The entire field of quantum mechanics was built upon such imaginative foundations. Erwin Schrödinger's cat, a creature both alive and dead, was never intended as a literal description of reality. It was a provocative thought experiment designed to stretch the limits of a theory, to force physicists to confront the bizarre implications of their own equations. Without that strange and unsettling image, the debate over quantum interpretation might have remained a technical footnote instead of the central mystery it is today. Thought experiments like this are the playgrounds where new physics is born. They allow us to test the boundaries of logic and intuition in a risk-free environment, revealing hidden contradictions and opening doors we did not know were there. Countless inventors and scientists credit their breakthroughs to this creative process. Nikola Tesla visualized his complex electrical machines with such vivid detail that he could supposedly build and test them entirely in his mind before constructing a single physical prototype. He saw speculation as a form of practical engineering. The chemist Auguste Kekulé discovered the ring-like structure of the benzene molecule after daydreaming of a snake biting its own tail, a symbolic image that unlocked a fundamental problem. These are not anecdotes of mere luck, they are testaments to a disciplined imagination, a mind trained to see connections where others see only data. Carl Sagan perfectly captured this spirit when he wrote, "Imagination will often carry us to worlds that never were, but without it we go nowhere." He celebrated our innate human drive to dream beyond the edge of the map, to ask the big, audacious questions about our cosmic origins and our ultimate fate. This celebratory curiosity is the very lifeblood of the search for quantum echoes. While we have no definitive proof of these parallel realities, the idea itself inspires a profound sense of wonder. It compels us to build more sensitive detectors, to refine our mathematical models, and to look at every unexplained glitch in a particle accelerator with fresh, hopeful eyes. Speculation plants the seeds for the evidence of tomorrow. It keeps the quest alive through the long years of negative results and dead ends, because the possibility itself is too compelling to abandon. We must, of course, balance this creative fire with the cool discipline of evidence-based reasoning. A beautiful idea must eventually face the harsh light of experimental verification. Speculation without grounding can drift into pure fantasy, but evidence without imagination becomes a sterile collection of facts. The two are partners in a dance, one leading with a question, the other following with a test. As we wholeheartedly embrace this creative process, allowing ourselves to wonder about the whispers from other worlds, we must also quietly prepare ourselves. The potential impact of confirming such echoes would ripple through every aspect of human existence, from our understanding of self to our place in the cosmos, forcing a transformation as profound as any in our history. The confirmation of quantum echoes would ripple through our civilization, reshaping its very foundations overnight. Our legal systems, built on the bedrock of a single, linear reality, would face unprecedented challenges. How does a court of law establish guilt or intent when every crime also exists in a state of not being committed across countless branches? A defense attorney might argue that their client, in another reality, made a different choice, raising profound questions about culpability and the very nature of justice in a multiverse. Legal scholars would need to pioneer a new framework, one that acknowledges the complex tapestry of possibility while still upholding moral responsibility within our specific branch. In education, textbooks would become dynamic portals. History lessons would no longer be a single narrative, but a braided river of what was and what might have been. Students would learn to think in probabilities, understanding their own lives as active choices within an infinite landscape. Science classes would begin not with facts, but with possibilities, nurturing a generation comfortable with ambiguity and interconnectedness. This shift mirrors the Copernican revolution, which dethroned Earth from the center of the cosmos. That discovery was initially met with fear and resistance, but ultimately it expanded our cosmic perspective and fueled the Enlightenment. The psychological adjustment for the average person would be the most profound. The knowledge that for every path taken, another you walks a different road could initially trigger an existential crisis or a deep sense of insignificance. Yet, this same knowledge can be a source of immense liberation. Futurists suggest we proactively foster cognitive resilience, teaching mental frameworks that help people see this not as a dilution of self, but as an expansion of being. The regret over a missed opportunity loses its sting when you understand that in another world, a version of you seized it. The anxiety about a single, wrong decision dissolves, replaced by the understanding that life is a spectrum of experiences, all equally real. How do we cultivate this openness, this cosmic flexibility? Sociologists point to the importance of narrative. We must learn to tell new stories about ourselves, not as solitary heroes on a single path, but as focal points of consciousness navigating a garden of forking paths. Support systems and public dialogues would be essential, helping people integrate this new reality into their personal identity and worldview. This preparation is not about having all the answers, but about building a society agile enough to ask the right questions. By confronting these implications now, we transform the potential shock of discovery into a conscious journey of empowerment. We stop being passive inhabitants of a single reality and become active participants in a cosmos of limitless connection. Even with these tantalizing clues, the hunt for definitive proof remains one of science's greatest challenges. We stand at the edge of a new frontier, armed with powerful theories but still searching for that first, irrefutable whisper. The central mystery that drives researchers is how to consistently detect a quantum echo. Our current detectors are marvels of engineering, but they are listening for a signal we cannot fully characterize in a universe filled with deafening noise. What would a repeatable, statistically significant echo even look like in the data? Would it be a specific energy signature, a unique pattern of quantum spin, or a gravitational tremor with no local source? Figuring out what to look for is half the battle. Another profound puzzle involves the laws that might govern any interaction between realities. If a branch of the multiverse can influence our own, even faintly, what principles control that exchange? Is it a form of quantum tunneling through the dimensional barrier, or a subtle gravitational leakage between cosmic bubbles? Understanding the rules of this potential crosstalk is essential to knowing where and how to search. A leading researcher at the Perimeter Institute for Theoretical Physics, Dr. Anya Sharma, often tells her students, the greatest mystery is not whether other realities exist, but whether they can ever speak to us. That question is what gets me out of bed every morning. Her sentiment is echoed in labs worldwide, where the drive to answer these questions is fueling a new generation of experiments. Over the next decade, a suite of ambitious missions will push the boundaries of our perception. The European Space Agency's planned LISA mission, a space-based gravitational wave observatory, could detect the faint ripples from collisions of supermassive black holes, but it might also hear the primordial hum of cosmic strings or the faint shudder of a long-ago collision with another universe bubble. Here on Earth, the next iteration of quantum computers with thousands of error-corrected qubits will act as unprecedented resonance chambers. Scientists at institutions like Google and IBM are already designing protocols to use these machines not for calculation, but for listening. They will run complex quantum processes in perfect isolation, watching for any minute deviation that suggests the process is being subtly influenced by its parallel counterparts in other branches. In deep underground laboratories shielded from cosmic rays, new arrays of ultra-cold quantum sensors are being constructed. These devices will monitor large masses of supercooled material, waiting for an inexplicable jitter, a vibration that cannot be attributed to any known force in our universe. Each of these projects is a testament to human ingenuity and our relentless drive to understand our place in the cosmos. The quest for quantum echoes is far more than a technical pursuit. It is a fundamental expression of human curiosity, a journey that pushes the very boundaries of knowledge and forces us to reconsider the nature of reality itself. We began this exploration by questioning the solidity of our everyday world, and we end it with a universe transformed into a vast, whispering tapestry of possibilities. We have seen how the bizarre rules of the quantum realm suggest a cosmos constantly branching, how the faintest echoes of those other branches might ripple through our labs, our history, and even our minds. The journey does not end here. It continues in every new experiment, every refined equation, and in your own sense of wonder the next time you feel a sudden intuition or a flicker of déjà vu. The cosmos is speaking, and we are only just learning how to listen. Our journey through the whispering corridors of parallel realities brings us to a final, humbling vista. We have ventured from the bizarre certainties of the quantum realm, where particles exist everywhere at once, to the radical possibility of an endlessly branching multiverse. We have searched for the faintest echoes in the precise data of particle colliders, and in the grand, cold spots of the cosmic microwave background. We have even explored how these ideas might resonate within our own minds, challenging our most personal sense of identity and our ethical responsibilities in a cosmos of infinite selves. The overarching revelation is that our universe is not a solitary, silent chamber, but a vibrant node in a network of unimaginable complexity, profoundly interconnected across all scales of existence. This is not a call for certainty, but an invitation to a perpetual state of wonder. The physicist Richard Feynman captured this essential truth when he admitted, "I think I can safely say that nobody understands quantum mechanics." His words are not a confession of failure, but a celebration of the mystery that lies at the very heart of science. It is the unknown that propels us forward, that keeps our questions fresh and our curiosity alive. The search for quantum echoes is far from over. It is a conversation that is just beginning. I encourage you to carry these questions with you. Read the works of the thinkers we have mentioned, from David Deutsch to Carlo Rovelli. Discuss these ideas with friends and ponder what they might mean for your own story within this vast tapestry of possibilities. Thank you for joining me on this extraordinary adventure to the edges of reality. I would love to hear your thoughts and reflections in the comments below. If you enjoyed this deep dive into the mysteries of the cosmos, consider subscribing for more journeys to the frontiers of space and science. The exploration continues, and the next great discovery could be just one curious mind